Joe. Because each data validator library has its own way of exposing the details of a data validation failure. For instance, in JavaScript AJV, the errors from the last data validation are stored as an array inside the validator instance. Theo. Why an array? Joe. Because there could be several failures. But let's start with the case of a single failure. Imagine we encounter a search book request where the title field is named My Title instead of Title. Take a look at this example. As you can see, we first instantiate a validator instance. Theo. And what does the information inside the errors array look like? Joe. Execute the code snippet. You'll see. When Theo executes the code snippets from listing 7.20, he can hardly believe his eyes. He looks at the details, finding the results hard to digest. Theo. I find the contents of the errors array a bit hard to understand. Joe. Me too. Fortunately, AJV provides an errors text utility function to convert the errors array in a human-readable format. See, for instance, what is returned when you call errors text. Theo. Let me see what happens when there are more than one validation failure in the data. Joe. By default, AJV catches only one validation error. Tip. By default, AJV catches only the first validation failure. Theo. I guess that's for performance reasons. Once the validator encounters an error, it doesn't continue the data parsing. Joe. Probably. Anyway, in order to catch more than one validation failure, you need to pass the All Errors option to the AJV constructor. Check out this code. Joe. We validate a search request with My Title instead of title and numbers instead of strings in the fields array. As you can see in the output of the code snippet, 3 errors are returned. Theo. Great! I think I have all that I need in order to add data validation to the boundaries of my system when Nancy asks me to make the library management system into a web server. Joe. Would you allow me to give you a small gift as a token of our friendship? Theo. I'd be honored. Joe takes a small package out of his bag, wrapped in a light green ribbon. He hands Theo the package with a solemn gesture. When Theo undoes the ribbon, he discovers an elegant piece of paper decorated with pretty little designs. In the center of the paper, Theo manages to read the inscription, JSON Schema Cheat Sheet. He smiles while browsing the cheat sheet. It's exactly what he needs. Then Theo turns the paper over to find that the back is also filled with drawings. In the center of the paper, he reads the inscription, An Example of Valid Data. Summary. DOP principle number 4 is to separate data schema and data representation. The boundaries of a system are defined to be the areas where the system exchanges data. Some examples of data validation at the boundaries of the system are validation of client requests and responses, and validation of data that comes from external sources. Data validation in DOP means checking whether a piece of data conforms to a schema. When a piece of data is not valid, we get information about the validation failures and send this information back to the client in a human-readable format. When data at system boundaries is valid, it's not critical to validate data again inside the system. JSON schema is a language that allows us to separate data validation from data representation. JSON schema syntax is a bit verbose. The expressive power of JSON schema is high. JSON schemas are just maps, and as so, we are free to manipulate them like any other maps in our programs. We can store a schema definition in a variable and use this variable in another schema. In JSON schema, map fields are optional by default. It's good practice to validate data that comes from an external data source. It's good practice to be strict regarding data that you send and to be flexible regarding data that you receive. AJV is a JSON schema library in JavaScript. By default, AJV catches only the first validation failure. Advanced validation is covered in Chapter 12. Chapter 8. Advanced Concurrency Control. No more deadlocks. This chapter covers atoms as an alternative to locks, managing a thread-safe counter and a thread-safe in-memory cache with atoms, managing the whole system state in a thread-safe way with atoms. The traditional way to manage concurrency in a multi-threaded environment involves lock mechanisms like mutexes. Lock mechanisms tend to increase the complexity of the system because it's not trivial to make sure the system is free of deadlocks. In DOP, we leverage the fact that data is immutable, and we use a lock-free mechanism called an atom to manage concurrency. Atoms are simpler to manage than locks because they are lock-free. As a consequence, the usual complexity of locks that are required to avoid deadlocks don't apply to atoms. Note: this chapter is mostly relevant to multi-threaded environments like Java, C#, Python, and Ruby. It is less relevant to single-threaded environments like JavaScript. The JavaScript code snippets in this chapter are written as though JavaScript were multi-threaded. Section 8.1. The Complexity of Locks. This Sunday afternoon, while riding his bike across the Golden Gate Bridge, Theo thinks about the Clafim project with concern, not yet sure that betting on DOP was a good choice. Suddenly, Theo realizes that he hasn't yet scheduled the next session with Joe. He gets off his bike to call Joe. Bad luck, the line is busy. When Theo gets home, he tries to call Joe again, but once again the phone is busy. After dinner, Theo tries to call Joe one more time with the same result, a busy signal. Obviously, Joe is very busy today, Theo tells himself. Exhausted by his 50-mile bike ride at an average of 17 miles per hour, he falls asleep on the sofa. When Theo wakes up, he's elated to see a text message from Joe. "See you Monday morning at 11 a.m.? Theo answers with a thumbs up and prepares for another week of work. When Joe arrives at the office, Theo asks him why his phone was constantly busy the day before. Joe answers that he was about to ask Theo the same question. They look at each other, puzzled, and then simultaneously break into laughter as they realize what happened. In an amazing coincidence, they'd tried to phone each other at exactly the same times. They both say at once, "A deadlock." They both head for Theo's office. When they get to Theo's desk, Joe tells him that today's session is going to be about concurrency management in multi-threaded environments. Joe: how do you usually manage concurrency in a multi-threaded environment? Theo: I protect access to critical sections with a lock mechanism, a mutex for instance. Joe: when you say access, do you mean write access or also read access? Theo: both. Joe: why do you need to protect read access with a lock? Theo: because without a lock protection, in the middle of a read, a write could happen in another thread. It would make my read logically inconsistent. Joe: another option would be to clone the data before processing it in a read. Theo: sometimes I would clone the data, but in many cases, when it's large, it's too expensive to clone. Tip: cloning data to avoid read locks doesn't scale. Joe: in DOP, we don't need to clone or to protect read access. Theo: because data is immutable? Joe: right. When data is immutable, even if a write happens in another thread during a read, it won't make the read inconsistent, because the write never mutates the data that is read. Theo: in a sense, a read always works on a data snapshot. Joe: exactly. Tip: when data is immutable, a read is always safe. Theo: but what about write access? Don't you need to protect that with locks? Joe: nope. Theo: why not? Joe: we have a simpler mechanism. It's called an atom. Theo: I am glad to hear there is something simpler than locks. I really struggle each time I have to integrate locks into a multi-threaded system. Joe: me too. I remember a bug we had in production 10 years ago. We forgot to release a lock when an exception was thrown in a critical section. It caused a terrible deadlock. Theo: deadlocks are really hard to avoid. Last year, we had a deadlock issue when 2 locks were not released in the proper order. Joe: I have great news for you. With atoms, deadlocks never happen. Tip: with atoms, deadlocks never happen. Theo: that sounds great. Tell me more. Tip: atoms provide a way to manage concurrency without locks. Section 8.2 Thread-safe counter with atoms. Joe: let's start with a simple case, a counter shared between threads. Theo: what do you mean by a counter? Joe: imagine that we'd like to count the number of database accesses and write the total number of accesses to a log every minute. Theo: okay. Joe: could you write JavaScript code for this multi-threaded counter using locks? Theo: but JavaScript is single-threaded. Joe: I know, but it's just for the sake of illustration. Imagine that JavaScript were multi-threaded and that it provided a mutex object that you could lock and unlock. Theo: it's a bit awkward. I guess it would look like this. Theo goes to the whiteboard. He writes what he imagines to be JavaScript code for a multi-threaded counter with locks. Joe: excellent! Now I'm going to show you how to write the same code with atoms. An atom provides three methods. Get returns the current value of the atom. Set overwrites the current value of the atom. Swap receives a function and updates the value of the atom with the result of the function called on the current value of the atom. Joe unzips a pocket in his laptop case and takes out a piece of paper. He hands it to Theo. Theo is pleasantly surprised as the sheet of paper succinctly describes the methods. Table 8.1. Theo: how would it look like to implement a thread-safe counter with an atom? Joe: it's quite simple, actually. Joe pulls out his laptop, fires it up, and begins to type. When he's done, he turns the laptop around so that Theo can see the code to implement a thread-safe counter in an atom. Theo: could you tell me what's going on here? Joe: sure. First, we create an empty atom. Then, we initialize the value of the atom with counter.set with 0. In the logger thread, we read the current value of the atom with counter.get. Theo: and how do you increment the counter in the threads that access the database? Joe: we call swap with a function that receives x and returns x plus 1. Theo: I don't understand how swap could be thread-safe without using any locks. Joe quickly goes to the whiteboard. He sketches the diagram in figure 8.1. Joe: you see, swap computes the next value of the atom, and before modifying the current value of the atom, it checks whether the value of the atom has changed during the computation. If so, swap tries again until no changes occur during the computation. Theo: is swap easy to implement? Joe: let me show you the implementation of the atom class and you'll see. Theo comes closer to the whiteboard. He modifies Joe's diagram a bit to make the flow of the swap operation more detailed. The resulting diagram is in figure 8.2. Theo still has a few questions, though. Theo: what is atomic compare and set? Joe: it's the core operation of an atom. Atomic compare and set atomically sets the state to a new value if, and only if, the state equals the provided old value. It returns true upon success and false upon failure. Theo: how could it be atomic without using locks? Joe: that's a great question. In fact, atomic compare and set is a compare and swap operation provided by the language that relies on a functionality of the CPU itself. For example, in Java, the java.util.concurrent.atomic package has an atomic reference generic class that provides a compare and set method. Note: see this link for general information about compare and swap operations. Implementations for multi-threaded languages appear in Table 8.2. Theo: apropos Java, how would the implementation of an atom look? Joe: it's quite the same, besides the fact that atom has to use generics and the inner state has to be stored in an atomic reference. Joe brings up a Java implementation of atom on his laptop. Theo looks over the code. Theo, what about using an atom in Java? Joe, here, take a look. It's quite simple. Theo takes a couple of minutes to meditate about this atom stuff and to digest what he's just learned. Then he asks Joe, Theo, what if swap never succeeds? I mean, could the while loop inside the code of swap turn out to be an infinite loop? Joe, no. By definition, when atomic compare and set fails on a thread, it means that the same atom was changed on another thread during the execution of swap. In this race between threads, there is always a winner. Theo, but isn't it possible that some thread never succeeds because it always loses the race against other threads? Joe, in theory, yes, but I've never encountered such a situation. If you have thousands of threads that do nothing besides swapping an atom, it could happen, I suppose. But in practice, once the atom is swapped, the threads do some real work, for example, database access or I/O. This gives other threads the opportunity to swap the atom successfully. Note: in theory, atoms could create starvation in a system with thousands of threads that do nothing besides swapping an atom. In practice, once an atom is swapped, the threads do some real work, for example, database access, which creates an opportunity for other threads to swap the atom successfully. Theo, interesting. Indeed, atoms look much easier to manage than locks. Joe, now let me show you how to use atoms with composite data. Theo, why would that be different? Joe, usually, dealing with composite data is more difficult than dealing with primitive types. Theo, when you sold me on DOP, you told me that we were able to manage data with the same simplicity as we manage numbers. Tip: in DOP, data is managed with the same simplicity as numbers. Joe, that's exactly what I'm about to show you. Section 8.3, Thread-Safe Cache with Atoms. Joe, are you familiar with the notion of in-memory cache? Theo, you mean memoization? Joe, kind of. Imagine that database queries don't vary too much in your application. It makes sense in that case to store the results of previous queries in memory in order to improve the response time. Theo, yes, of course. Joe, what data structure would you use to store the in-memory cache? Theo, probably a string map where the keys are the queries and the values are the results from the database. Tip: it's quite common to represent an in-memory cache as a string map. Joe, excellent. Now, can you write the code to cache database queries in a thread-safe way using a lock? Theo, let me see. I'm going to use an immutable string map. Therefore, I don't need to protect read access with a lock. Only the cache update needs to be protected. Joe, you're getting the hang of this. Theo, the code should be something like this. Joe, nice. Now let me show you how to write the same code using an atom instead of a lock. Take a look at this code and let me know if it's clear to you. Theo, I don't understand the function you're passing to the swap method. Joe, the function passed to swap receives the current value of the cache, which is a string map, and returns a new version of the string map with an additional key-value pair. Theo, I see, but something bothers me with the performance of the swap method in the case of a string map. How does the comparison work? I mean, comparing two string maps might take some time. Joe, not if you compare them by reference. As we discussed in the past, when data is immutable, it is safe to compare by reference, and it's super fast. Tip: when data is immutable, it is safe and fast to compare it by reference. Theo, cool. So atoms play well with immutable data. Joe, exactly. Section 8.4, State Management with Atoms. Joe, do you remember a couple of weeks ago when I showed you how we resolve potential conflicts between mutations? You told me that the code was not thread-safe. Theo, let me look again at the code. Theo takes a look at the code for the system data class that he wrote some time ago, repeated in listing 8.8. Without the validation logic, it makes the code easier to grasp. It takes him a few minutes to remember how the commit method works. Suddenly, he has an aha moment. Theo, this code is not thread-safe because the system consistency.reconcile code inside the commit method is not protected. Nothing prevents the two threads from executing this code concurrently. Joe, right. Now can you tell me how to make it thread-safe? Theo, with locks? Joe, come on. Theo, I was kidding, of course. We make the code thread-safe not with a lock, but with an atom. Joe, nice joke. Theo, let me see. I'd need to store the system data inside an atom. The get and set method of system data would simply call the get and set methods of the atom. How does this look? Joe, excellent. Now for the fun part. Implement the commit method by calling the swap method of the atom. Theo, instead of calling system consistency.reconcile directly, I need to wrap it into a call to swap. So, something like this? Joe, perfect. Theo, this atom stuff makes me think about what happened to us yesterday when we tried to call each other at the exact same time. Joe, what do you mean? Theo, I don't know, but I am under the impression that mutexes are like phone calls and atoms are like text messages. Joe smiles at Theo, but doesn't reveal the meaning of his smile. After the phone deadlock yesterday, Theo's pretty sure that he and Joe are on the same page. Summary. Managing concurrency with atoms is much simpler than managing concurrency with locks because we don't have to deal with the risk of deadlocks. Cloning data to avoid read locks doesn't scale. When data is immutable, reads are always safe. Atoms provide a way to manage concurrency without locks. With atoms, deadlocks never happen. Using atoms for a thread-safe counter is trivial because the state of the counter is represented with a primitive type, an integer. We can manage composite data in a thread-safe way with atoms. We make the highly scalable state management approach from Part 1 thread-safe by keeping the whole system state inside an atom. It's quite common to represent an in-memory cache as a string map. When data is immutable, it is safe and fast to compare by reference. In theory, atoms could create starvation in a system with thousands of threads that do nothing besides swapping an atom. In practice, once an atom is swapped, the threads do some real work, for example, database access, to provide an opportunity for other threads to swap the atom successfully. Chapter 9. Persistent Data Structures. Standing on the Shoulders of Giants. This chapter covers the internal details of persistent data structures, the time and memory efficiency of persistent data structures, using persistent data structures in an application. In Part 1, we illustrated how to manage the state of a system without mutating data, where immutability is maintained by constraining ourselves to manipulate the state only with immutable functions using structural sharing. In this chapter, we present a safer and more scalable way to preserve data immutability, representing data with so-called persistent data structures. Efficient implementations of persistent data structures exist for most programming languages via third-party libraries. Section 9.1. The need for persistent data structures. It's at the university where Theo meets Joe this time. When Theo asks Joe if today's topic is academic in nature, Joe tells him that the use of persistent data structures only became possible in programming languages following a discovery in 2001 by a computer researcher named Phil Bagwell. In 2007, Rich Hickey, the creator of Clojure, used this discovery as the foundation of persistent data structures in Clojure. Unveiling the secrets of these data structures to Theo in a university classroom is a way for Joe to honor the memory of Phil Bagwell, who unfortunately passed away in 2012. When they get into the university classroom, Joe starts the conversation with a question. Footnote 1. P. Bagwell, Ideal Hash Trees. Available at www.edu/. epfl.ch/papers/ideal hashtrees.pdf. Joe, are you getting used to DOP's prohibition against mutating data in place and creating new versions instead? Theo, I think so, but two things bother me about the idea of structural sharing that you showed me. Joe, what bothers you, my friend? Theo, safety and performance. Joe, what do you mean by safety? Theo, I mean that using immutable functions to manipulate data doesn't prevent it from being modified accidentally. Joe, right. Would you like me to show you the naive way to handle immutability or the real way? Theo, what are the pros and cons of each way? Joe, the naive way is easy but not efficient, although the real way is efficient but not easy. Theo, let's start with the naive way then. Joe, each programming language provides its own way to protect data from being mutated. Theo, how would I do that in Java, for instance? Joe, Java provides immutable collections, and there is a way to convert a list or a map to an immutable list or an immutable map. Note: immutable collections are not the same as persistent data structures. Joe opens his laptop and fires it up. He brings up two code examples, one for immutable lists and one for immutable maps. Theo, what happens when you try to modify an immutable collection? Joe, Java throws an unsupported operation exception. Theo, and in JavaScript? Joe, JavaScript provides an object.freeze function that prevents data from being mutated. It works both with JavaScript arrays and objects. Joe takes a minute to scroll through his laptop. When he finds what he's looking for, he shows Theo the code. Theo, what happens when you try to modify a frozen object? Joe, it depends. In JavaScript strict mode, a type error exception is thrown, and in non-strict mode, it fails silently. Note: JavaScript's strict mode is a way to opt in to a restricted variant of JavaScript that changes some silent errors to throw errors. Theo, in case of a nested collection, are the nested collections also frozen? Joe, no, but in JavaScript, one can write a deep freeze function that freezes an object recursively. Here's another example. Theo, I see that it's possible to ensure that data is never mutated, which answers my concerns about safety. Now, let me share my concerns about performance. Tip: it's possible to manually ensure that our data isn't mutated, but it's cumbersome. Joe, sure. Theo, if I understand correctly, the main idea behind structural sharing is that most data is usually shared between two versions. Joe, correct. Theo, this insight allows us to create new versions of our collections using a shallow copy instead of a deep copy, and you claimed that it was efficient. Joe, exactly. Theo, now here is my concern. In the case of a collection with many entries, a shallow copy might be expensive. Joe, could you give me an example of a collection with many entries? Theo, a catalog with 100,000 books, for instance. Joe, on my machine, making a shallow copy of a collection with 100,000 entries doesn't take more than 50 milliseconds. Theo, sometimes even 50 milliseconds per update isn't acceptable. Joe, I totally agree with you. When one needs data immutability at scale, naive structural sharing is not appropriate. Theo, also, shallow copying an array of 100,000 elements on each update would increase the program memory by 100 kilobytes. Joe, indeed, at scale we have a problem, both with memory and computation. Tip: at scale, naive structural sharing causes a performance hit, both in terms of memory and computation. Theo, is there a better solution? Joe, yes. For that, you'll need to learn the real way to handle immutability. It's called persistent data structures. Section 9.2, the efficiency of persistent data structures. Theo, in what sense are those data structures persistent? Joe, persistent data structures are so named because they always preserve their previous versions. Tip. Persistent data structures always preserve the previous version of themselves when they are modified. Joe, persistent data structures address the two main limitations of naive structural sharing, safety and performance. Theo, let's start with safety. How do persistent data structures prevent data from being mutated accidentally? Joe, in a language like Java, they implement the mutation methods of the collection interfaces by throwing the runtime exception unsupported operation exception. Theo, and in a language like JavaScript? Joe, in JavaScript, persistent data structures provide their own methods to access data, and none of those methods mutate data. Theo, does that mean that we can't use the dot notation to access fields? Joe, correct. Fields of persistent data structures are accessed via a specific API. Theo, what about efficiency? How do persistent data structures make it possible to create a new version of a huge collection in an efficient way? Joe, persistent data structures organize data in such a way that we can use structural sharing at the level of the data structure. Theo, could you explain? Joe, certainly. Let's start with the simplest data structure, a linked list. Imagine that you have a linked list with 100,000 elements. Theo, okay. Joe, what would it take to prepend an element to the head of the list? Theo, you mean to create a new version of the list with an additional element? Joe, exactly. Theo, well, we could copy the list and then prepend an element to the list, but it would be quite expensive. Joe, what if I tell you that the original linked list is guaranteed to be immutable? Theo, in that case, I could create a new list with a new head that points to the head of the original list. Theo goes to the classroom blackboard. He picks up a piece of chalk and draws the diagram shown in figure 9.1. Joe, would the efficiency of this operation depend on the size of the list? Theo, no, it would be efficient no matter the size of the list. Joe, that's what I mean by structural sharing at the level of the data structure itself. It relies on a simple but powerful insight. When data is immutable, it is safe to share it. Tip. When data is immutable, it is safe to share it. Theo, I understand how to use structural sharing at the level of the data structure for linked lists and prepend operations, but how would it work with operations like appending or modifying an element in a list? Joe, for that purpose, we need to be smarter and represent our list as a tree. Theo, how does that help? Joe, it helps because when a list is represented as a tree, most of the nodes in the tree can be shared between two versions of the list. Theo, I am totally confused. Joe, imagine that you take a list with 100,000 elements and split it into two lists of 50,000 elements each. Elements 0 to 49,999 in list 1, and elements 50,000 to 99,999 in list 2. How many operations would you need to create a new version of the list where a single element, let's say element at index 75,100, is modified? It's hard for Theo to visualize this kind of stuff mentally. He goes back to the blackboard and draws a diagram. See figure 9.2. Once Theo looks at the diagram, it's easy for him to answer Joe's question. Theo, list 1 could be shared with one operation. I'd need to create a new version of list 2 where element 75,100 is modified. It would take 50,000 operations, so it's one operation of sharing and one operation of copying 50,000 elements. Overall, it's 50,001 operations. Joe, correct. You see that by splitting our original list into two lists, we can create a new version of the list with a number of operations in the order of the size of the list divided by 2. Theo, I agree, but 50,000 is still a big number. Joe, Indeed, but nobody prevents us from applying the same trick again, splitting list 1 and list 2 into 2 lists each. Theo: how exactly? Joe: we can make list 1.1 with elements 0 to 24,999, then list 1.2 with elements 25,000 to 49,999, list 2.1 with elements 50,000 to 74,999, and list 2.2 with elements 75,000 to 99,999. Theo: can you draw that on the blackboard? Joe: sure. Now it's Joe that goes to the blackboard. He draws the diagram in figure 9.3. Theo: let me count the number of operations for updating a single element. It takes 2 operations of sharing and 1 operation of copying 25,000 elements. Overall, it takes 25,002 operations to create a new version of the list.